18.17 is now the formation of acetals. So what is an acetal? An acetal is like that hydrated form that we showed you, but this time we have a diether or a geminal ether. I've never heard it called that, but that technically is what it is. Rather than having the hydrate, and instead of using water, we're using an alcohol. Okay, so these are types of, it's what's called an acetal, okay, or a ketal, I guess you can call it ketals, but they're mostly called acetals. Okay, mechanism same way. This protonates. The first equivalent comes in and attacks, kicks up the pi bond. This protonates again, and then another one comes in and kicks out water. Okay, I don't remember if I have the mechanism on here, but if I don't, we will definitely do the mechanism in class. Okay, actually, there you go. There's the mechanism. Never mind. Don't worry about this thing, this OTS. Just O plus. Okay, this grabs O plus, protonates. Okay, here's that equilibrium thing where these electrons can pop up. Water, or I'm sorry, your alcohol attacks. Proton gets popped off to form what's called a hemiacetal. Hemi meaning half of an acetal. Half of it is an OR group, the other half is an OH. Okay, well now we need to get rid of this OH. So you can imagine this is going to protonate to give you a water molecule. That's going to leave to give you another plus charge, and then another alcohol is going to attach there. That's basically what happens. So I believe the next, actually, you know what, they don't show it. I thought they were going to, oh yeah, here it is. Here's your OH group. It protonates to give you a water molecule. That comes out. What actually happens is one of these lone pairs pop in and kick out the water to form this intermediate. Okay, again, I don't like how your book does this. Okay, so then you have water. Or not water. You can have another alcohol come in and kick up those electrons. That's kind of what they're showing here, but they're showing it on this molecule that I don't like. All right, so you know, I'd rather you do it like this, have that attack, and that pops up. But you know what, honestly, I don't care if you do it the other way, as long as you understand what's going on. And then alcohol deprotonates to form your acid catalyst, and there is your acetal. Okay. Okay. Let's just talk about this first. Here's a hydrolysis of acetals. This is to go backwards. This is once you have an acetal, what can you do with it? Well, they're kind of used as protecting groups. They protect functional groups. I'm going to show you an example. But this acetal, to take off acetals, you just do the exact opposite because it's a reversible reaction. And a little bit of acid and a lot of water, you can then remove it. The mechanism is the exact reverse of how to put it on. Okay, so I'm going to let you kind of work on that, and we'll talk about it in class. We'll kind of work on it together in class. All right. Here's just a fancy example of an acetal. Instead of two different alcohols, your alcohol is connected to the same compound. Okay, so ethylene glycol, and you form this kind of five-membered ring. Kind of for shorthand, let me actually just show you what we do for a shorthand. You don't have to draw out the whole entire thing, but what we do for shorthand is you just draw that like that. Okay, so the skeletal structure. All right, this is the same thing as this, right? And your product looks like that. Okay, I had a student once call it a Bart-Simpson reaction because if you do this, that kind of look like Bart Simpson. Yeah, man. Hey, dude. Okay. Anyways, moving right along. So it's called an acetal, and that's the reaction. So addition of a diol produces a cyclical acetal. The reaction is reversible. The reaction is used in synthesis as protecting carbonyl groups. Okay, so here's one way of doing it. Let's say you have this compound, this ketoaldehyde, okay, and you want to reduce the ketone, but you don't want to do anything to the aldehyde. So let's say you want this as your product. Let's say you want this. Okay. Now, if you were to try to add sodium borohydride to this, what's going to happen? It's going to reduce this first, and then it's going to go ahead and reduce this. So kind of, in fact, you might even have some of this first and then the aldehyde first. You might get a mixture. You know, you might get a keto alcohol, an aldehyde alcohol, or a dialcohol, a diol. Okay, so is there any way to kind of take this out of the equation, protect this somehow, then do your chemistry on the ketone, and then go back and get back your aldehyde? And the answer is yes. That's what acetals are kind of used for, protecting groups. Since my aldehyde is more reactive, if I use the Bart-Simpson reaction, protect the carbonyl, okay, what I can then do is I can then go ahead and add sodium borohydride, reduce the ketone to the alcohol, and then remember the acid and water removes the acetal to form the aldehyde. So that's kind of what it is. So the acetal will not react with sodium borohydride, so it just reacts with the ketone, and then hydrolysis pops it off. Okay? So that's kind of a common place for aldehydes. I know I skipped a few of these slides. You can read these. Hydrolysis easily in acid. Aldehydes are more reactive than ketones. We talked about that. Formation. Yeah, this is stuff that we already talked about. The other thing I want to talk about is where else do you see acetals? Okay, you actually see this in carbohydrates. Okay, this is really the main place. A lot of people think, well, this is kind of so obscure. Well, it's really not. Okay, sugar molecules. A lot of you have seen probably a sugar molecule that looks like this. This is what's called a Hawthorne projection. If we have time to talk about carbohydrates in our class, we'll talk about them. But this is kind of a structure of a sugar, and you can see this carbon right here, okay, is a hemiacetal. You got an OH, and it's attached to this oxygen, which is attached to a carbon. So carbohydrates have this. This is a main thing. This is glucose. This is a main structure of glucose. If you look at other sugars, okay, if you look at sugar, I'm not going to put all the other stuff, but like if you look at fructose, looks something like this. All right, it's a 6-membered ring with all its OHs. I'm not going to write it because there's no point in writing it. This is now a acetal. Okay, your carbon right here is an acetal. You got an oxygen attached to a carbon and another oxygen attached to a carbon. So these acetals are actually, found a lot in nature. All right, anytime you have a sugar, which is pretty much almost every biological system inside of our body probably utilizes a sugar of some sort. Okay, so it's very commonplace in biology. Oxidation of aldehydes, this is review 2. Sodium dichromate with a little bit of acid can oxidize aldehyde. This reaction, the one with silver, Ag2O, is called a Tollens reagent. Tollens. Okay, it oxidizes aldehydes to a carboxylic acid. Okay. Our next lab, or the lab after that, we're going to do what is called a Qualitative Analysis Lab. What's a Qualitative Analysis Lab? Before we had IRs and NMRs, how do you think people would analyze their compounds to determine if they made a compound? So let's say that they're doing an oxidation and they want to form an aldehyde. How do they know that they formed an aldehyde if an IR and NMR haven't been existed yet? Well, they do another chemical reaction on their compound. They isolate their compound, they do a chemical reaction on it that just works for aldehydes. Okay, an example is a Tollens test. Tollens is a silver oxide. Let me go back to it. And what happens is the oxygen oxidizes the aldehyde to the carboxylic acid, and you just form silver metal. So silver is your product as the metal, solid, okay, which is obviously shiny. All right, and what you actually form is what's called a silver mirror. Okay, so on this next slide kind of shows you this is the Tollens test. This is what happens. You actually form the silver on the inside of your flask, and it's a mirror. You can actually kind of see the guy that's like taking the picture of this. He probably used this in front of it to like block himself out, but you can see the silver formed on the glass. Okay, so this is something that we're going to do in class. It's kind of a fun lab because it kind of shows you how in the long time ago, more than 100 years ago, this is how they used to analyze compounds. They would do this, and if they got that mirror test, they knew that they had their aldehyde. Okay, so that's another oxidizing agent. Reducing agents, I'm going to go through this quick. Sodium borohydride for secondary. Sodium borohydride for ketones and aldehydes. LAH for everything, but mostly for carboxylic acids and their derivatives. Also, hydrogenation can reduce carbonyls. Okay, so here's the sodium borohydride examples. We've seen this 100 times already. LAH, again, can reduce them, but they also mostly reduce acids and esters. It is very challenging to handle, so use sodium borohydride if you don't have to use LAH. The hydrogenation, this catalyst is called Rainy nickel. Rainy was the name of the guy who invented this. It's basically the element nickel with hydrogen absorbed onto it. Okay. Now, the thing about Rainy nickel, though, is the thing about hydrogenation is that if you have more than one functional group that has a pi bond, it reduces all of your pi bonds. Okay. So Rainy nickel will reduce your carbonyl, but it'll also get rid of your double bond, your carbon-carbon double bond. Okay, if you just wanted to reduce this, then you would use sodium borohydride or LAH, because those won't touch the double bond. Okay, so but it's used in industry. It's very clean. It's very easy to purify. I don't think it's that expensive either. All right. So, and then the last two reactions we're going to talk about is the Clemenson and the Wolff-Kishner. The Clemenson we talked about last chapter. That was with zinc and mercury amalgam with hydrochloric acid. It gets rid of carbonyls. Notice it goes from a carbonyl to a CH2 group. A Wolff-Kishner is another type of reaction that does this. Okay, first here's the Clemenson. We've seen this before. Zinc and mercury to HCl. It gets rid of your carbonyls. Notice right here, your carbonyl is gone. You have hydrogens. Same thing for the aldehyde. Here in the cyclohexanone, you get hydrogens. The Wolff-Kishner, though, goes through this hydrazone. Remember, I told you we're going to see, we talked about this imine. Remember, this is an imine. Okay, so this imine, you form the imine. You then, in the presence of potassium hydroxide and water, you get rid of this. You form nitrogen gas. Okay, and water, and you can get rid of the carbonyl. Okay, so here's the example. The mechanism, we're going to talk about the mechanism of this in class. I'm sure it's in the book if you like to look in the book, or if you want to try to figure something out, just but basically what happens is your base keeps plucking off your hydrogens here. Plucks off a hydrogen, forms a nitrogen double bond. This then grabs a hydrogen from water, and it does it a second time. That's basically what the mechanism is, but we will go over it in class. Okay, so it forms a hydrazone. Then with heat and strong base, you can do the reaction. The solvent, this just talks about the solvent. It's not something we really have to worry about, but usually you have to put this in high boiling solvents. You need to boil this thing about over 150 degrees for it to occur. So ethylene glycol, that's kind of what actually they're showing here, diethylene glycol. Ethylene glycol is antifreeze, so it's kind of thick, has a lot of hydrogen bonds, the boiling point is pretty high, and DMSO is a kind of a common solvent. Okay, so that is it for this chapter. And we will talk more about it when we see each other in class.